All right, so today we talked about a few things I want to review with you. And if we take a look at this, here is Rutherford's gold foil experiment where he shot alpha particles through the gold foil. And as it went through the gold foil, most of the particles landed here, letting us know that the atom is made mostly of space. And some of them got deflected, which suggested that the alpha particles that were deflected, they were, first of all, they were only small angles, and that let us know that the nucleus is a positively charged uh, particle, since the alpha particle is also positively charged. And if we take a look at the ones that bounce all the way back here, then it lets you know that the nucleus carries of the most of the atom's mass right at the center of the nucleus, where the atoms are made mostly of space, where the center of the atom is positive, mass of the atom is in the nucleus. So what do we have? We have a model. We have the beginning of a model, right? And what is a model but a simplified version of what actually exists, right? And so we have this center of the nucleus where we know we have positive charges. How do we know that? Well, this is how we know that, right? And we know that there's these, the atom is somewhat larger. We know that this is, and we know that most of the atom is empty space. This is all empty space in the atom. The center has the positive charges. That's what we know. Now we look at electrons and know, well, how do we know anything about electrons? Well, we have this cathode ray tube, which we discussed in class, kind of drew it. And you see, actually, you can actually see this in actual cathode ray tube. You see the beam of what's called a cathode ray. And as the cathode ray shoots through this tube, you can see it on the fluorescent background. As you move the magnet here, the beam of electrons gets pulled up towards the positive end of the magnet. So what that tells you, as we said in class, is from this experiment we learned that electrons were negative. After decades of study and hundreds of experiments, we were able to construct a model of the atom, the model of the atom that we use today. Okay, so we know that the atom's nucleus contains protons, and the protons have a positive 1 charge, right? So they have a positive charge. They have a mass of 1 AMU, and we talked about what AMU is. That's atomic mass unit. Now, I need you to remember that when we're talking about protons and neutrons and electrons and the atom, that the model that we're describing is based on numerous experiments, and I've only described 2 of them to you. There are a lot of famous scientists involved in the history of this model, this discovery, this concept. And so when we study the atom, we're talking about the result of hundreds of experiments and several careers and generations. So 1 charge, protons have a plus 1 charge, neutrons have no charge, and remember my zeros have a slash so you can tell the difference between O's and zeros. Have no charge, and have a mass of 1 AMU. Now that's important because the fact that they have a mass of 1 AMUs is a big deal, and we'll talk about why. You'll see why in a minute. And then electrons. Those are the 3 basic components of the subatomic particles that make up an atom. Now, of course, all of these we know by way of physics that they're made up of much tinier things, but This is what we're talking about when we're talking about chemistry. We just need to know enough chemistry to get into the biology. So electrons. And electrons have a -1 charge. And the interesting thing is they only have 1/2000th of a AMU. So it takes 2,000 electrons to equal 1 proton. So we say that the electron's mass is negligible. And remember, negligible means we know it has mass, but its mass is not great enough to impact the mass of the entire atom to any great extent. So as we move on and we start to think about the atom as a whole, the effect of the electrons on the mass of the atom, again, is something that we can ignore or we can neglect or is negligible. All right, so in any case, let's go ahead and take a look at the atom as we know it, putting together all the knowledge that we have. There's protons in the center, there's neutrons in the center. All right. That forms the nucleus. We know that the nucleus is small, but because we're not going to draw it to scale, it's not going to look that small. It's really tiny, so it would be a small dot in the middle of this giant atom, but we're not going to go ahead and draw that. We're going to draw it big so that we can see the inside. And then it has these shells, these electrons that go around it, and these electrons go around in these shells. These are called energy levels. And the electrons move in these energy levels from one energy level to the next. They don't go much further, they don't go much closer. And they have inside these energy levels these things we call orbitals. So we know all this information. Again, there's many experiments that have proven it, but we're going to go ahead and just accept this and summarize it here. So they have the orbitals are the shapes of these the paths of the electrons. And you have to understand when I speak of the electrons' paths, we're talking about probabilities of the motion of the electrons, and they can be predicted mathematically. Although they can be predicted mathematically, there's a certain level of uncertainty. But we just accept that. And there's a lot of other aspects of the atom that we're really not going to be able to cover in this course. But we are going to talk about electrons and their paths. And their paths take on shapes. And we call these shapes within the shell, we call these things orbitals. And so it'd be S and P. And there's D and F, but we're not going to worry about that. This is not a chemistry class. We're going to focus on biology. Also, one other thing we need to remember is that when we're looking at this is a model. So this is a model, an atomic model. The model does not really represent all the details, all the aspects of the atom. In fact, it only deals with specific characteristics. Only deals with distance from the nucleus for the path of the electrons. It only deals with shape for the electrons' paths. It really doesn't deal with. First of all, let's look at the fact that it doesn't deal with its three-dimensional state. The S and the P actually does deal with it a little bit. This drawing is two-dimensional, but the atom is actually three-dimensional. It goes into and out of the screen that you're looking at. As I said, a tiny nucleus compared to the path of the electrons. And the path of the electrons are not these concentric circles. They're actually more of a cloud, and that's what we call an electron cloud. So this is a different model. This model is the electron cloud model. The electron cloud model, though, would not be very useful for our discussion of the paths of the electrons. It's more accurate as far as its description of the electron's path, but it doesn't help us in discussing chemical bonding, for instance. So we know that the atom actually looks more like this, but we go ahead and we use this because this is more useful. It's very similar to Newton's laws of motion versus Einstein's laws of relativity. Just the idea that Einstein's laws that govern quantum mechanics and large-scale motion are more accurate, but they're not as useful as Newton's laws because of where we are, our scale, and how easy they are to use. It's the same with the electron cloud model. Sure, this is more accurate, but this model allows us to discuss chemical bonding in a much easier and useful way. So that's why we're using this model. This particular model is also known as the Bohr model, and named after the scientist Niels Bohr, who first developed it. So this Bohr atom or Bohr model is actually very useful when we start to discuss bonding, and then that'll lead us into the Lewis model, which gets rid of, and each step, I want to say, each model then simplifies a lot of the things that we do know about the electron, about the atom, and just looks at one or two aspects, which lets us then discuss what's important for the problem that's at hand. All right, let's go ahead and move on from here. So before I do move on, let's review. Protons have positive charge, so 1 AMU. Atomic mass unit is what AMU stands for. Neutrons have 0 charge, 1 AMU. Electrons have a -1 charge, 1/2000th of an AMU. Because it's 1/2000th of an AMU, we say it's negligible, right? We say, hey, we can ignore this. We can ignore this. It's so small that we can ignore it, okay? Then we have this idea that there's models. Each model is useful for a different aspect or different problem that we're looking at. So we talked about the idea that these atoms, as we're looking at them, when they're coming together, and that's what we're talking about here, that's what it comes down to. Two atoms are coming together and they're moving towards each other. When they get close, and they never actually touch, right? When they get close, they're going to repel each other. They're going to move away from each other. Why? Because on the outside of the atom, as we should understand by now, are these electrical charges, and they're negative charges. And we know that the force that's pushing them away is the strongest force outside of strong force. Is the strongest or one of the strongest of the fundamental forces, right? So as they come, this electromagnetic force, as soon as they get close to one another, they're going to want these two atoms are going to want to repel. So the question has come up: what holds them together? What makes them stick? What holds you together? If these things are always repulsing each other, always pushing each other away, what holds them together? Okay, so let's take a look at that, and let's look at an example. And let's look at the example of oxygen gas, or oxygen, the element oxygen. Let's remember the element oxygen, and let me get rid of this and say, let's remember that the element oxygen always has eight protons. The element oxygen always has 8 protons. And if we look at the mass of oxygen, it's 15.9994, I believe it is. In any case, we'll come back to this later, but you have an atomic number of 8, or 8 protons. That defines the element. So we have to remember that defines the element. I mentioned this several times. So if we have 8 protons in the center here, plus 8, and we go ahead and we look at the orbitals, the shells, right? Now there's something to these shells that we haven't discussed yet, so be ready for it. It gets a little more complicated. we're only going to discuss the first two energy levels or shells. If we have two of these oxygen atoms, there's 2 plus 8s. And we're not going to worry so much about the isotopes right now. What we're worried about is this center atom, the number of protons. The fact there's plus 8 protons means that we can hold, that atom can pull in 8 electrons. And if it's going to pull in 8 electrons, so the electrons are white, let's say. If it's going to pull in 8 electrons, the very first thing it does is the first 2 get pulled in as close as they can possibly get. And that would be in the first energy level. And so this is the first energy level 1. And it only has one orbital, one shape, and that's the S. 1s. The 1s can only hold 2 electrons. The next energy level actually has 2 different orbitals. And so this is 2. This is energy level 2. And energy level 2 has a 2s and a 2p. And so the 2s can hold 2 electrons. And the 2p can hold 6 electrons. Together, the second energy level can hold 8 electrons. And that's why we call this a full octet when we talk about the rules of when these two energy levels have all 8 filled in, we call it a full octet. And so when we talk about the rules of bonding, we talk about 2 very, very, very important rules. And the rules of bonding go as such. The first is that all particles are move towards neutrality. They all want to be neutral. And the second is that all atoms are trying to get a full octet. They're not really trying, they just move towards it because it's less energy, it's more stable. But these two aspects, these two rules, really drive chemical bonding. So you really need to understand them and how to apply them in order to be really safe and not make mistakes. So let's go ahead and take a look at what happens when we start to form bonds, and why is it that we form bonds. To do that, you must remember these two rules. It's incredibly important you remember these 2 rules. And also that this energy level holds 2, this holds 6, and this holds 2. That's also important. All right. So now let's take a look at these 2 oxygens. The first oxygen atom, as I said, has 8 protons. The second oxygen atom also has 8 protons because all oxygen atoms have 8. So they have these orbitals, and 2 electrons come in. The 8 protons are going to pull in using their electromagnetic force, electrostatic force. They're going to pull in 2 electrons because they have 2 plus charges. Everything wants to be neutral, right? They're pulling in 2 electrons, right? And so, that's if it had 2. But now we have 8 protons. So we don't have 2 electrons. We have 2 protons. We have 8 protons. So altogether, it's pulling in 8 electrons. All right, so there's 2 electrons are taken up. So 2 more have to fit in, and they have to jump up to the next energy level to fit. So here's another electron, and this was the 1s. This is the 2s. The 2s can only hold 2 electrons. There's your 2. So altogether, right now we have 4. The next electrons that get pulled in have to come in at the next energy level, next orbital. The only way they're going to fit, and that energy level, that orbital, is the 2p. Okay. So now we have 4, so we need another 4. So that's 1, 2, 3, 4. So we need to fill in the other the other. How many? How many are missing? Well, let's figure this out. So right now that's all 8, and if we do the same thing over here, the first, the second, the third, so that's 1, 2, 3, 4, 5, 6, 7, 8, right? That's all 8 electrons and 8 protons. But let's look at the outer energy level. Let's look at the outer energy level and ask ourselves, do these two? These two have 8. They're balanced. They're neutral, right? 8 pluses. Let's do the math. 8 pluses. 8 pluses here. Let's count them. 8 pluses. Get you 8 negatives. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 positives equals 1, 2, 3, 5, 6, 7, 8. And so if we do the math and we say 8 protons are positives minus 8 electrons, why minus, because that's the charge of the electrons. The 8 positives cancel out the 8 negatives and you have a 0 charge, right? So these two oxygen atoms are indeed neutral. So that's rule number 1 is satisfied. The next question is do they have a full octet? Now you got to remember the energy level is the second energy level, not the orbital. So how many electrons does it have in the second energy level? That's 1, 2, 3, 4, 5, 6. So they have 6 electrons in the outer energy level. Same thing here, right? Because they're duplicates. So what's going to happen? How can you possibly end up with both of these neutral atoms? So they stay neutral, but at the same time, they get a full octet or 8 electrons. The way they do it is they share. They share the electrons they do have. So what happens is if you share these two, and remember, sharing is something we're not really used to doing. So when you share, you're not giving. They don't really give the electron. One doesn't give the electrons to the other. They share them. So my wife and I share a car. How many cars do I have? I have 1 car. My wife, how many cars does my wife have? She has 1 car. So when we share, when we're talking about sharing in this sense, we're not talking about splitting them up. We're not talking about somebody getting them and somebody not. We're talking about these two being shared equally. So this atom has 2, these two both, and these 2 electrons count for this atom as well. So now let's go ahead and count. Now we've made 1 bond. This is a bond. The sharing of these electrons holds these 2 together. Every time they move away, they get pulled closer to each other. There's this kind of back and forth dynamic equilibrium where these 2 kind of stay together because of this sharing of these electrons. And so we see here where we have these 2 electrons. So let's count them. Let's count them for this atom. 1, 2, 3, 4, 5, 6, 7. Excuse me, we have to count the outer shell. So 1, 2, 3, 4, 5, 6, 7. So that's 7 for this atom. And 1, 2, 3, 4, 5, I'm sorry, 1, 2, 3, 4, 5, 6. Am I missing something? Did I mess up? Do I count 8 here? Let's see. Hold on a second. I think I messed up here. 1, 2, 3, 4, 5, 6, 7, 8. So all 8 are there. 2, 2. All right, so I should have 1. Oh, I see what I did. It's my count that's red. I told you they share and I didn't think about it. So let's count how many electrons this atom has. It's 1, 2, 3. I'm sorry, 1, 2, 3, 4, 5, 6, and 7. So this atom also has 7. So both of these have 7. But is 7 the same as 8? Is 7 mean that they have a full octet? What is the outer shell? Now remember, we're talking about the outer shell, and I just mentioned, we saw earlier that the outer shell is a 2s and the 2p. The S can hold 2 and the P can hold 6. Together they hold 8 electrons. So we need 8, and right now we have 7. We're missing one more. What can we do? What can these two atoms do to complete their octet? Well, they can share another pair of electrons. So now they're sharing 2 pairs of electrons. So now let's go back and count the electrons again. 1, 2, 3, 4, 5. 1, 2. Almost did it again. 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 electrons on this side. Let's check. And again, counting. Let me go ahead and number them. 1, 2, 3, 4. Use a different color. They're starting to all blend together. 1, 2, 3, 4, 5, 6, 7, 8. So this also has 8 electrons. So these two count. These 2 electrons here count for both atoms, and these 2 count for both atoms are sharing. When we draw the bonds, we just simply draw an oxygen double bonded to an oxygen. All the other structures are assumed. We know that the structures are there, but it's easy, isn't it easier just to go ahead and draw this? Let's take another look at. Let's take a look at some other examples, and then maybe even look at carbon and see what kinds of bonding patterns we can see with carbon, since carbon is one of those 9 elements that you really should know. Okay, so I'd like to take a look at some of the exceptional atoms. And an exceptional atom is this hydrogen. Hydrogen is strange, and the reason hydrogen, it's actually, if you look at the periodic table, we find hydrogen in an odd place. It's up here. You'll notice that its color is different from all the colors, all the other colors, all the other elements in this column. This column has all pink, but then you have this blue up here. And that's because, again, hydrogen is just this strange character. Hydrogen has only 1 proton. So 1 proton. And most of the hydrogens have no neutrons at all. So it's interesting, the atomic mass unit then, the mass of hydrogen is usually just 1. And we know that it's actually 1.0 something because there is heavy hydrogen, right? So hydrogen could have 1 proton and 1 neutron, right? So this is, what do we call this when we have an element that's not like the majority? This is the majority of them. No, we don't call it a minority. The element that's not like the majority of its fellows is called an isotope. So they're rarer, right? And the isotope, 1 proton and 1 neutron, does exist, but the majority of hydrogen has only 1 proton by itself. That has consequences. So let's say you're trying to get hydrogen, which has 1 little proton. There it is. In fact, instead of writing the proton like that, let me just go ahead and put the number 1 like we did in the other. So here's your nucleus with 1. And you have another hydrogen over here with 1 proton. So 2 hydrogens. An average element, an average hydrogen element. How many electrons would you expect this proton to have, this atom to have? We'd expect it to have 1 electron. We'd expect it to have 1 electron, right? Because how many electrons could this 1 proton pull in? Only 1. So as these two come together, they want to fill their octet, but there's a trick here. There's a really, really kind of interesting trick. That's that the octet for this hydrogen, for this 1 proton and no neutrons, and only 1 electron each of these atoms, these 2 hydrogens, these lonely little partners, can't pull in more than one more, can they? But that doesn't matter because their outer shell doesn't hold 8. Their outer shell only holds 2. They have a 1s. That's all they have, a 1s. And because they have a 1s, their full octet, I know we call it an octet because of 8, but there are exceptions to this rule, and hydrogen is one of them. Because we have a full octet, that octet is known this octet is actually filled in by just 2 electrons. A full octet for hydrogen is only 2. So, how are these 2 hydrogen going to get 2 electrons? They can't pull any more electrons in. Why? They only have a 1. They only have 1 proton. They can't pull another electron in. They're not strong enough. So what they do what the oxygens did. They share these 2 electrons. And when they share, the interesting thing is that now they have a full octet. So how many electrons does this atom have? This first atom? Well, there's 1 electron here and 1 here. So they have 2. And how many electrons does this atom have? 1 electron here, 1 here. They have 2. Remember, that's what sharing means. Now, 1s is the outer shell, and it can only hold 2, so it's full. So hydrogen is satisfied. And that's why we write hydrogen gas. And if we rewrote it in the line diagram, it would look like this. And as it turns out, that is hydrogen gas. And we saw that in the lab. So that's our hydrogen gas. Let's go ahead and take a look now at another aspect of this chemistry, of this bonding business. Before I tell you about this model that we call Lewis dot, the Lewis dot model is actually, we saw the Bohr model, we just looked at it. And the Bohr model, again, BOHR, that's this idea. I'm going to go ahead and pick an atom. And I'm going to go ahead and pick an atom 8, oxygen again. The Bohr atom would say 8, and then it would say 2, and then it would have, in the 2s, it would have another 2. That's 4. And the 2s, I'm sorry, in the 2p, it would have 1, 2, that's 4, 5, 6, 7, and then 8, right? So it'd have 8 electrons in total. And that's what the Bohr atom would look like, something like that. So that's fine, but that doesn't really help us as much as the Lewis dot structure does. And then we'll look at why Lewis dot. This is yet one more researcher came up with this idea. He noticed something about somebody noticed something about the periodic table. I believe it was Lewis. He said, "Look, we're worried about the outer shell when these 2 atoms come together, right?" He said, "We're only worried about the outer shell in chemistry. The inner shell's affected subtly, and yes, in a lot of parts of chemistry, you worry about all the sublevels, all the shells, and there's a lot of interesting chemistry that deals with that. But when we're talking about when we're talking about bonding, it's really the outer shell that's the most important. And that outer shell usually holds 8. Sometimes, like in hydrogen, it can only hold 2. Why don't we draw the outer shell, and only the outer shell, since that's really the only thing we're concerned with most of the time?" So Lewis said, "All right, well, I know that the groups, except for this center group, we're not going to worry about the center group, but you'll notice that most of the atoms of life, except for iron and a couple of the others in the transition metals, most of the atoms of life are not found here. Our most important elements that we have to concern ourselves with in biology are carbon and oxygen and sulfur and phosphorus and hydrogen and sodium and chlorine, right? So really, those are the ones that we have to really concern ourselves with. Again, I mentioned 9 because You can consider calcium a little bit and some magnesium, some of the minerals that we need as vitamins and supplements to our enzymes. But in any case, oxygen, obviously important, carbon, nitrogen, phosphorus, sulfur, hydrogen, sodium, and chlorine are all follow this rule that I'm about to say. Hydrogen, I think I mentioned hydrogen, yes, including that. So everyone in this column is part of group 1. Every one of the elements in this column have only one valence electron. Every element in this column only has 2 valence electrons. In this column 3, in this 4 and 5 and 6 and 7. So every one of these A's, the number tells you the valence electrons. That's why noble gases don't react, by the way, very easily. They don't react very easily because they all have a full octet already, all by themselves. See, helium has 8 valence electrons. So they have a full octet. They don't need to do much else. So let's take a look at Lewis dot and do this and see what we can do with just knowing this and drawing a very simple, again, the simplest model that allows us to focus just on what happens when two atoms come together. Let's do that hydrogen model again. Here's hydrogen. Here's hydrogen. And here's hydrogen. 2 hydrogens come along. What group is it in? It's in group 1. Here it is, group 1. So I only need to put 1 dot. There's 1 dot. Now I know that hydrogen is in its 1s, so I know it only has 1 dot. But I also know that hydrogen can come together and make 1 bond. I draw it with the stick instead of this circle. I can draw it like so. And if I want to draw it the way we would in a chemical reaction, we would draw it like so. That's what that little 2 means. There's 2 of them bonded together. And this is what the bond is. Now we can do the same thing with bigger atoms. Remember what we did with oxygen? We drew all those dots. Well, why don't we go ahead and try that oxygen thing again? What if 2 oxygens come together? And how many valence electrons are in each? Well, there's 6 valence electrons in oxygen. Every one in this column has 6. So let's put our dots. 1, 2, 3, 4, 5, 6. Let's put our dots. 1, 2, 3, 4, 5, 6. Well, how many bonds do we need? I need to share enough to get 8 in both. Well, this would give each of them an extra one. 2, 4, 2, 4, 5, 6, 7. 2, 4, 5, 6, and 7. So that's 7 electrons. We need another bond. So here's these 2 sharing now. Double checking. 2, 4, 5, 6, 7, 8 for this one. We can check this one off. Check. And the other one, 1, 2, 4, 2, 4, 5, 6, 7, 8. So this one then can be checked off as well. And so now let's go ahead and take this diagram. See how much simpler that was? That was much simpler than drawing all those concentric circles. This just allows us to make these, look at the chemistry of that's going on without having to worry about all the other electrons and balancing the protons and the electrons and whatever else is going on. So let's go ahead and take a look at what happens next. So we would go ahead and draw it as a stick model. We'd have that going on, but there'd be 2 lines because there's a double bond. This double stick would actually mean it's oxygen with 2 oxygens bonded to each other. So oxygen gas and hydrogen gas. And we looked at that in our lab. So could we use this to make a new molecule? Is it possible then? There's some other combination, because right now we're looking at pure gases, right? By the way, this is all called covalent bonding. So here we're just talking about bonding where there's sharing going on, or that means that it's sharing electrons. They're sharing electrons. There's another kind of bonding called ionic bonding we'll talk about later. But right now, all the covalent bond examples I've given you is when the same one element's bonded to itself. Can elements bond to other things? Well, I picked hydrogen and oxygen on purpose because we reacted them in the lab. We did a lab and we reacted them and you saw the results. So let's go ahead and look at what we did, and let's look at it with this Lewis dot structure in mind. So what we did in the lab is we took hydrogen gas and we added it to oxygen gas. I'm writing the balanced equation here. And we yielded, and it's reversible, but I'm going to put it in one direction, H2O. Now there's two oxygens on this side, only one on this side, so I have to double this. That means two waters, right? Two whole water, this whole thing, there's two of them. But that also means now there's 4 hydrogen, so we have to put a 2 in front of this one. So every 2 hydrogens and one molecule, every molecule of hydrogen, every 2 molecules of hydrogen bond with 1 molecule of oxygen to form 2 molecules of water. So let's take a look at what that would look like. Well, what does that look like? Well, that would look like this. Hydrogen gas bonded to hydrogen gas plus oxygen gas bonded to oxygen gas yields water. That's hydrogen and hydrogen. 2 hydrogens bonded to 1 oxygen. And there's 2 of these. There's 2 of these. And there's 2 of these, right? Okay. How'd that happen? Well, let's do the Lewis dot structure. See if it works out. See if it makes sense as far as a stable octet. We know oxygen has 8 electrons, 8 protons total, 8 electrons total, but only 6 of them in the outer shell. How do we know that? We know that from the periodic table. It's in group 6, right? But we also know it if we did the Bohr atom, we could work it out. You knew from the very first example, as we start filling in the electrons in the Bohr model, that the first shell needs 2, so we had 8. 8 minus 2 is 6. So that's what's left over, and those had to fill it in the second shell. All right, so we take a look at this. Again, looking at the shortcut of using the periodic table, we know oxygen has 6. So let's go ahead and just draw our 6 little dots representing electrons. So that's 2, 3, 4, 5, and 6. So we have these 6 electrons sitting here, and we know we need 8. We have 2 hydrogens available, hydrogen here and a hydrogen here. And each of them have 1. Does it make sense that this water is produced? Will this be a stable molecule? Well, if we share here, this atom has 2 electrons, and that's all it needs for its outer shell because it only has a 1s. So we're good with that one. That one's stable. This atom has 2 electrons, so it's stable. We're ready to go. This, ooh, gee, I messed that up, sorry. Let's draw that again. Oxygen, again. Let's say oxygen, that's 1, 2, 3, 4, 5, 6. And let's draw a hydrogen with 1 and a hydrogen with 1. And if we drew our circle, we see this one has 2. These 2 are being shared by this hydrogen. It's happy. These 2 are satisfied. The octet rule is happy. It's not charged. It has a full octet. Everything's fine. Now let's check and count for the oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has its 8 electrons. It's happy. Check. So all the 3 atoms are happy when it forms water. We know hydrogen's happy because we just did it. We know oxygen's happy because we did it before. And the new molecule water is happy as well. And this indeed is a chemical reaction, the chemical reaction we looked at, where we looked at this water that's being formed by mixing hydrogen and gas with a little spark. Don't forget our spark, because this is both a combustion and and a synthesis, where two things are coming together to form one, and it's a combustion because oxygen is being used. It's releasing a lot of heat and light, right? So a lot of energy is being released with a small bit of energy being added to it. In our example, it was a flame, right? We just added a flame to hydrogen in the presence of oxygen, and we got water. And that is a chemical reaction, and all of these are covalent bonds. They're all sharing. All right. Well, we're going to leave ionic bonding for tomorrow. It's an interesting discussion. There's some, and we did use some ions in class in the lab, so we should discuss it and make sure you understand what you were looking at. I hope this helped. Your course, I don't expect you to watch it tonight, but hopefully you'll have a chance to watch it before too long, before the weekend, and I'll have another ionic bonding little video sent to you soon. All right, bye.